Okay, welcome to my presentation on an efficient cyber evidence sharing using zero-knowledge proofs. Myself, Arman, Zand, and my supervisor, Cardiff. Next page. We just go over a bit of a background and protocol review, components, results, and a bit of a summary and discussion. Next slide, please. So we propose a scheme that allows participants to establish verification of mutual information using existing methods. We combine Merkel trees and zero-knowledge proofs, short for ZKPs, to achieve this. And the scheme is applied to digital forensics and cybersecurity scenarios, where two parties that cannot disclose private information wish to verify if there is any common knowledge. We provide a method of using ZKPs for more efficiently verifying large number of data. So with ZKPs, and usually it's used for an identity, checking the identity of someone, but when there is a lot of proofs, we have a look into that. So we define cyber evidence sharing as the task of verifying mutual knowledge of confidential information or digital evidence without disclosure. Current solutions are constrained, lengthy and bureaucratic processes which would benefit from cryptography, and they're constrained and lengthy because you're involved in a third party with a third party, and you could face some potential scrutiny or some security practices or some disclosure of information. And we propose to use cryptography using openly published security solutions, and the cryptography in question is the zero-knowledge proofs. And also, we'd like to note that this project was implemented in order to test the performance. The method of constructing the proof is not complex and does not require some specialist knowledge in order to be implemented correctly. So there's less mistakes to happen, which is quite a big deal when implementing some cryptography. So some previous work on the sharing of cyber intelligence, cyber evidence, does not really involve any cryptographic methods. So for example, listserv, which is a kind of mailing list system, very simple way, information sharing and analysis centers, ISACs, information sharing analysis organizations, and sovereign nations will also have national cyber centers that work with the private sector. It is also worth to note that there is some privately developed solutions and models that are not openly published. These are more ad hoc for some companies. So we have a brief look at the protocol, a high-level overview. We have Department V and Department P. So we have a verifier and approver, respectively, and they want to check if there is some mutual information between them. But in this cybersecurity scenario, we check that both parties begin with the same base information. So at the beginning, one of them sends out a base information check, and they send each other the proof of knowledge and verify that there is the same information. And after a while, the data set changes. They populate them with TTPs, tactics, techniques, and procedures, for example, in the cyber intelligence field. And after a while, they do a check again, and they send a proof of what knowledge they have, and they can check again what mutual information verify their mutual information and realize any actions that they can take. Next slide, please. Now we'll go over the components. We have Merkel Trees, which is quite a well-known binary tree, efficient representation of a data structure. So very briefly, as you can see in the little diagram below, is that if you split up your data into blocks A, B, C, and D, you can concatenate two of them reciprocally, and they will create this tree. And you can check from the top down. So for example, if you compare two trees and, for example, block C is different, then you can make your way down the tree, and you can see in bold that you don't have to check the other parts. So it's efficient to notation of O log 2n for an n depth binary tree. And what we do here, especially with the Merkel trees, that instead of the node making up of the hashes of the data blocks, they are instead zero knowledge proofs, which I'll show you in a bit. Next slide, please. So why use zero knowledge proofs instead of hashes? Well, zero knowledge proofs is a way of proving immediate knowledge to a verifier without disclosing information. A proof is generated, and the verification process will output either true or false. It uses uniformly chosen random value to generate different outputs, proofs for the same input. So the thing with hashes is you don't really need to know the input of the hash. You can just obtain it and send it off without really knowing what the input of it was. But with ZKP, since you're using a random value to generate a different proof every time, you're proving that you know the input as well. And there's three main aspects to zero knowledge proofs. Is that there's the zero knowledgeness, the confidentiality is kept for the information that needs to be proved. Completeness, the verifier will have confidence that the prover knows the information that they didn't reveal. And soundness, that there cannot be an instance where false information can be verified. I can also note that with hashes, you can kind of brute force, you can compare hashes much easier if you know the input of one of them. So in our protocol, they start with the base information. And if something changes a bit, they could do an educated guess at what the change was, and they can compare the hash again. And specifically, our ZKP scheme that we use is the non-interactive shared Shimi identity scheme. And thank you. And we'll just have a quick look at the methods of creating a proof and verifying it. So in bold, I've just made a high-level description of what the functions do. So a create proof function takes input data and outputs two values. The values is the proof and will be different every time, even for the same input. The prover and the verifier will want to prove some knowledge X. So if you know a bit about modular exponentiation, it's fine, but don't worry, you just need to know that at the high level description of the function. But with this random value that the prover chooses, it computes values R and C, and that is what makes up the proof, as you can see. And also just a quick note here is that compute in C is a hash of the concatenated values of G, Y, and T. And yeah, next slide, please. And then these two values will be part of the input of the verify function. So the verify function inputs the proof of the two values and data to compare. This will output true if the proof matches with the input data, or false if not. So this R and C value that we just mentioned is also an input with the input data. And the verifier will compute his own hat T and hat C value and compare if that was the same as the C value that he's received from the prover. And the interesting thing about this is the exponentiation of the V minus Cx. And that is a method that's also being used in Schnorr's digital signature scheme. Next slide, please. So in this section, we'll just discuss the results, the protocol design, and the performance. So in this higher level, in this more detailed, description of the protocol, with department V for verify and department P for the prover. Here I just note that we use the Merkel tree and the create proof function. So if you take those functions and imagine that it takes all of the blocks of the tree and converts all of the nodes of the tree and converts them into zero knowledge proofs, and it performs the verify function on them as well. So at the beginning, again, they verify that they have the same information. And afterwards, the data set changes by it being populated with their own information. And they do a check again if they have some mutual information, and they can check the differences that they have from that. So here you can see that we use a verify function on the Merkel trees, on the binary trees, and there is a interaction where it doesn't have to be the verifier that initiates after the changes occur, it can be the prover as well. Next slide, please. So I've implemented, we've implemented this in C# using the standard tools provided in the .NET library, and the create proof method uses a hash function, which is the secure hash algorithm 256, and I used the arbitrary precision integers from the big integer library. And that's important because we'll go into specific numbers of, if you show me the next slide, please, the performance of the scheme. So here I just want to give an idea of how fast how long it takes to create a proof, and also how long it takes to verify one. So it takes just about 2.5 milliseconds to create a proof and 3 1/3 milliseconds to verify one. So it's quite fast. But if we have a lot of proofs to check, how efficient can it be? So next slide, please. So we have a comparison of a simple linear list. So imagine that we do a verification of 500 records or so, and we go through all of them one by one, so in a simple loop throughout the whole of the list to verify each of the records. And then we compare that with the binary tree, the Merkel tree, where the nodes are replaced with the zero knowledge proofs. And you can see the pattern that it is indeed logarithmic. And even when there is more differences, so more leaf nodes are different, where it has to check more paths, random paths, it's still more efficient when there is large number of records. Next slide, please. Now we'll just do a bit of a summary and discussion. So we've used the zero knowledge proof scheme that allows parties to efficiently compare mutual information without revealing said information. And the zero knowledge proof scheme is used in a way that it makes verification of large amount of data more efficient. And also to note that we've used this scheme in the application of cyber evidence sharing, where normally there is not a cryptographic solution in this field, and we found that maybe it would benefit from not having a trusted third party, and having this more peer-to-peer interaction would prevent or would give confidence to parties to try and verify mutual information with each other, so that they don't face any kind of scrutiny or be worried about disclosing sensitive information. And the thing about the Merkel tree is that it can mirror the hierarchy of the input data set, so it's flexible that way. And also to note is that our proposed scheme works in a semi-trusted environment, which may be vulnerable to eavesdropping by an overarching entity. But ZKP, the zero knowledge proof scheme themselves, are quite secure. So it's an improved security over the hashes, as we've mentioned before. And the disclosure of information is something that's not something to be as worried about. And now ZKP schemes can also be a bit more complex than the one that I've showed, such as the zero knowledge proof scheme called the ZK-SNARK, and that stands for zero knowledge succinct non-interactive argument of knowledge. So it's quite a mouthful, but essentially it creates the proof based on the computation that produces a certain output. So that means that you can compare a procedure and its output without revealing what it was. And originally that was derived from Microsoft's Pinocchio protocol at Microsoft Research, and was taken and improved by the cryptocurrency community, which, for example, Monero and Zcash, they use that for making their cryptocurrency more privacy orientated. It's a powerful scheme, but we argue that it's a bit complex, and that the non-interactive fiat scheme is lightweight and easy to implement. And with that said, the further improvements on anonymity and use of more complex zero-knowledge proof schemes in our protocol would add functionality and consequently more applications, such as comparing the procedures I just mentioned. So comparing procedures like scripts or viruses and things like that. And that is it. Thanks for listening. I think I'll take some questions.